Dr. Anuj Jadda, Senior Professor, Department of Chemistry, Chemical Engineering and Biological Sciences and Bioengineering, IIT Jammu. Respected Principal of the College, Dr. S.P. Sarswat, Dr. Nazir Hussain, Department of Medical Chemistry, Banaras Hindu University, Varanasi, Dr. Gurpreet Kaur, Research Assistant, School of Chemical Engineering, University of New South Wales, Sydney, Australia, Dr. S.K. Pandey, Professor of Chemistry, University of Jammu, Dr. Meena Sharma, Professor of Chemistry, University of Jammu, distinguished participants, faculty members, heads of the various departments of this college, dear students, ladies and gentlemen, a very good morning to one and all. On behalf of Government College for Women, Parade Road, Jammu, I cordially welcome you all to the inaugural ceremony of the two-day international conference on recent advances in chemical sciences, which has been organized by the Department of Chemistry of Parade College in collaboration with Cape Comoran Trust, Tamil Nadu, India. We had planned to organize this conference both via online and offline mode, but due to surge in COVID cases, we have shifted to online mode only. I extend my deep gratitude to Dr. Anuj Jadda for having accepted our request to grace the occasion as chief guest and keynote speaker also. Madam, I welcome you with great reverence and look forward to having your advice and blessings on this occasion. I welcome Dr. S.P. Sarswat, worthy principal of this college, who takes keen interest in various academic activities and whose invaluable guidance and support has helped us in organizing this conference on recent advances in chemical sciences. He has been the source of constant encouragement and inspiration for all of us. I also extend a warm welcome to Dr. Nazir Hussain from the Department of Medical Chemistry and BHU Varanasi, and Dr. Gurpreet Kaur from University of New South Wales, Sydney, Australia, who in spite of their busy schedule are here with us as plenary speakers of this international conference. A special welcome to Dr. Ijaz Ahmed Dar, Associate Professor from the Department of Chemistry, University of Kashmir, and Dr. Princey Gupta from the Department of Chemistry, Central University of Jammu, who will be the chairpersons for today's technical sessions. As convener of the conference, I consider it a great privilege and honor to share with you that the college was established on 1st of June 1944 as Maharani Mahila College through Mahila Education Society, which is a registered body of the then prominent and respectable women of Jammu. It was taken over by Government of J&K on 25th of November 1953 and was renamed as Government College for Women, Parade Ground, Jammu. On 15th of September 2014, the college was granted autonomous status by University Grants Commission and by the University of Jammu. At present, the college is the autonomous institution of the University of Jammu. So far as the Department of Chemistry is concerned, the Department of Chemistry of this college was established in the year 1965 and offers chemistry as an elective subject at undergraduate level and is hosting the conference of international level for the first time. Nowadays, chemical science has emerged as a basic and latest tool for all kinds of technical research, education, and allied subjective collaborative work among various leading branches of science. Day by day, various techniques and instrumentations encompassing innovations are rapidly coming forth, and such trends are changing the nature of chemistry as a discipline, the role of chemists, and the landscape within which we work. Modern sophisticated instrumentation techniques play a key and reliable role for the characterization, structure determination, and identification of new molecules. On the basis of these inventions, we can modify our work according to the need of our industry and for the betterment of the society. Considering these facts, we have organized this international conference on recent trends in chemical sciences with topics and sub-themes: nanochemistry, green chemistry, catalysis, solid-state chemistry, material chemistry, bioinorganic chemistry, and bioorganic chemistry, etc. So this conference will bring broad range of topics under one roof and provide the participants an overview on the current developments in chemistry. The conference will provide a platform for the researchers from diverse areas of chemistry to come together and exchange their ideas and explore the theme of the conference. We have also asked our undergraduate class students, especially of the final year class, to participate in the conference so that they can keep themselves abreast with the recent advances in chemical sciences. On day 1 of the conference, there will be a keynote address by Dr. Raju Chadha and 2 plenary lectures by Dr. Nazar Hussain and Dr. Gurpreet Kaur. Besides, there will be 2 technical sessions for paper presentation, and in each technical session, some 8 or 9 presentations will be there. So in the end, I once again extend hearty welcome to our esteemed chief guest and all the participants of the conference. Thank you very much. Over to Gurpreet.
Thank you very much, sir. Thank you very much. The conceived thought of transforming this conference into reality would not have turned up without the unending motivation, support, and unconditional cooperation of our visionary principal, Dr. S.P. Saraswat. I would request sir to please share his words of wisdom regarding the conference. Sir, over to you.
Thank you, Gurpreet. Worthy Chief Guest, Professor Anju Chadha, Senior Professor, Department of Chemistry, Chemical Engineering, Biological Sciences and Bioengineering, IIT Jammu. Dr. Nazar Hussain, Department of Medicinal Chemistry, BHU. Dr. Gurpreet Kaur, Research Assistant, University of New South Wales, Australia. Then, distinguished participants, faculty members, dear students, ladies and gentlemen, a very good morning to one and all. We had planned to host this conference in both online as well as on offline mode, that is a blended mode, simultaneously, but the worsening COVID situation has stopped us from doing so, and therefore we are here via online mode only. The Department of Chemistry, Government College for Women, Breakdown Jammu, is organizing this conference on recent advances in chemical sciences. As you know, chemical sciences is involved everywhere and is the need of the hour to keep updating the scientific community from time to time with this ever-evolving science. Chemistry, like all other scientific fields, has changed significantly in the last half century. From classical sciences, chemistry has broadened its scope into biology, medicine, physics, material science, nanotechnology, computation, advanced method, large-scale processor development of drugs, and whatnot. The applications of chemical compounds, materials, and knowledge have also dramatically increased. The consequences of chemistry are far-reaching. Chemistry has been largely responsible for shaping society as we know it, from developing stronger materials for large-scale construction down to cosmetic products which we use every day. In fact, the society has been benefited beyond description from advances in the field of chemical science. The industrial applications of chemistry have also benefited our daily lives. What we eat, what we wear, our transport, the technology that we use, how we treat illnesses, how we get electricity, to name just a few. Considering these facts, this international conference on recent advances in chemical sciences has been organized. This conference will bring a broad range of topics under one roof and will provide the participants an overview on the current developments in chemistry. I hope the deliberations of the conference will go a long way in inculcating the scientific temper among all stakeholders, especially the young scholars and the students. In the end, I congratulate the organizers of the event and express my sincere gratitude to the chief guests, speakers, and students for joining this conference. Thank you.
Thank you very much, sir. Now, I would like to introduce our chief guest and the keynote speaker of the conference, Dr. Anju Chadha. She is a senior professor in the Department of Chemistry, Chemical Engineering and Biological Sciences and Bioengineering at Indian Institute of Technology, Jammu since September 2021. After retiring from the Department of Biotechnology at IIT Madras as an institute chair professor in June 2020. All through her research and teaching has been in the interdisciplinary area of chemical biology. She did her master's in organic chemistry from the University of Pune in 1977, taught in Foundation College Pune for a year, and then went for her PhD to the Department of Organic Chemistry, Indian Institute of Science, Bangalore in 1984. For her postdoctoral work, she was a Fujaki Fellow and then a visiting associate at NIDK, Bethesda, USA, and a Bold Fellow from 1992 to 1993 in the University of Wuppertal in Germany. She worked for 6 years in the pharma industry with research and development before joining IIT Madras as faculty in the Department of Chemistry in 1998. In December 2021, she was awarded the Rosalind Franklin Medal from the Indian Chemical Society, Kolkata. She was awarded the SK Chatterjee Award in 2015 as an ISA alumni and an International Women Day Award by University of Madras for her outstanding contribution to the science and technology. Professor Anju is featured as one of the 100 women scientists of India in the book Leelavati's Daughters. The running theme of her research is biocatalysis, which includes use of enzymes in organic synthesis and organic mechanism, especially green chemistry, biodiesel, biotechnology, and biosensors. She has mentored many PhD, MSc, MTech, and BTech, and even young school students. She has published more than 120 research publications and is a reviewer for projects of international repute, for example, in Switzerland and Qatar. She has been the first member secretary of Institutional Ethics Committee at IIT Madras. Anju ma'am, welcome to you this conference. Please share your research work and your experience in the field of research of chemistry. Anju ma'am, over to you.
Good morning, everybody, and namaskar. It's an absolute pleasure to be here and an honor to be invited by this wonderful college of history of which I have been going through. Thank you again, Gurpreet and the principal for this really privileged invitation. I hope I'm one of those who really deserves this honor. Morning, and it's a wonderful sunny morning in Jammu, right? And you know, I'm sitting in IIT Jammu in my office and I can view the beautiful Trikuta hill with a little bit of snow. What could be better? So welcome to all the young friends, the young students, and of course, probably I'm one of the senior people in this conference. So I can call everybody younger than me. And what I'm planning to do today is tell you about my work, which is largely on using biocatalysts for organic reactions. You can use microbes to make wonderful molecules for you through the help of enzymes. And if you use the word biotransformation, you will see that it means different things to different people. The use of biological systems to create more efficient, more selective, environmentally friendlier processes when you feed in a raw material to get industrial products so that problematic chemical transformations become easier. That is one definition. It could be xenobiotic or drug metabolism. It could be bioremediation. It could be just biocatalytic enzymatic reactions. But the sum total of this is that you need to use a microbe or a living cell or enzyme to transform a raw material into a valuable material. So this is where the basis is. Now, why did we want to do that? In a bit, I'll tell you why it's important, but let's look at the history of this. You know, wine and beer fermentation is as old as 6000 BC in Egypt, and also bread, 4000 BC in Egypt. Both these processes used microorganisms. Yeast cells were used in wine fermentation in a more systematic way in 1850s by Louis Pasteur. Lactic acid was industrially produced by microbes, 1880, USA. And finally, this Moritz Straub decided that these reactions were actually being done by proteins, which are the biological catalysts. Finally, in 1907, this particular finding that yeast, which is used in ethanol fermentation, actually contains a protein, got the Nobel Prize to Buchner. Eventually, acetone was produced by a microorganism during World War I, penicillin, during World War II and amino acids as recent as the 60s. Enzymes have been used over the second half of the 20th century following characterization of many enzymes. And if you look at this, glucose isomerase, GI, it is used in the manufacture of high fructose corn syrup, an industrially important enzyme. Cannase is used in the leather industry. Protease is used in the detergent industry, also for digestion. So there are many uses of these biocatalysts. I've already told you about detergents, but there's a very recent enzyme known as the Taq polymerase, which is used in PCR or polymerase chain reaction. And today we are using RT-PCR throughout the globe because of the pandemic to diagnose the disease. So enzymes are here to stay and they are very valuable biocatalysts. The penicillin and the steroid industry particularly are important because they rely heavily on microbial transformations. Now, if you look at this quote, Lord, I fall upon my knees and pray that all my syntheses may no longer be inferior to those conducted by bacteria. This is a quote from Scientific American of 1981. And you see here it says that there is a frustrated organic synthetic chemist who looks at bacteria and says that they are so efficient in making so many molecules all together in the cell just so that life goes on. May our synthesis also be as efficient. Synthetic organic chemistry, of course, has impacted every aspect of modern living, but it still needs to improve. You have so much question about the efficiency, the scalability, cost effectiveness, affordability, preservation, improvement, and of course, the ever problematic harsh chemicals and conditions which harm the environment. That is more important today than anything else. And Nicolau, the famous, very important and famous chemist of our times, this time, has said that it is also important to re-emphasize that organic synthesis has a long way to go before it can be considered competitive with biosynthesis, nature's way of making molecules. The standards of nature, that is close to 100% yield, little if any waste, ambient temperature, aqueous media, should be those that we must seek in our drive to perfect our synthetic capabilities in order to enable the myriad of imaginable and unimaginable applications of organic synthesis of today and tomorrow. He is a synthetic chemist and he realizes it's a little late for him. I think he's about 70 plus, maybe 80. And he's saying that now, as recently as 5 years ago. But I hate to admit this, but organic chemists have never really acknowledged that nature is really the supreme chemist. Can you imagine as you sit there and listen to me as I talk, we are all breathing, respiration is going on, circulation is going on, digestion is going on, all is being done by these fantastic biocatalysts or enzymes. Now, if that is the case, then why are we not looking at these enzymes? If nature is so supreme, why don't we use these methods? It's about time that we looked at them. And if you look at this, it's not that people are not using them, but more people should use them. And in organic synthesis, you really need to incorporate some of their properties. And if biocatalysts by themselves could be microbial, you can use a whole cell. Microbial, by the word itself means it is micro, you need a microscope to see it. It could be cell-free. You can break a cell and get the enzymes out. Cell extract based, you can use the crude cell mix after breaking the cell, or you can purify an enzyme. Traditional enzymatic or cell-free biosystems. This is the latest. I will not touch that. People are using cell-free biosystems for biomanufacturing. It requires a lot more infrastructure and is expensive. But if you look at the traditional whole cells, you will see how wonderfully you can work them to make us really happy with what they do. So if you now look at what the cell is really doing, it is using what is called an enzyme. All of us are with full of enzymes, and each cell has close to about 3,000 enzymes. Can you believe that? All of them very specific, doing their own job without getting into the way of others. And typically, very simply put, an enzyme has a very defined three-dimensional structure. It has an active site where the substrate must fit and to be turned into a product after forming an enzyme substrate complex. They work near neutral pH, in water, standard temperature, pressure, are stereo, chemo, regio specific, they are biodegradable and are very efficient. Nobody can beat carbonic anhydrase. No man-made catalyst has a turnover of anything close to 10 raised to 6 per second. What that means is that this enzyme can give you in 1 second 10 raised to 6 molecules of the product. But they're all catalysts. They only reduce activation energy. They do not disturb the equilibration of the reaction. So you can see with enzyme, you have much less activation energy. Without the enzyme, it is a bigger hill you have to cross. So I've convinced you that these are fantastic biocatalysts. Now, if I need to tell you a little bit about the structure. There are 4 different levels or hierarchies of the structure. I'll start from the bottom, the primary structure, which is just a string of alpha amino acids put together through peptide bonds in a very, very defined stereochemical way, because all are L amino acids generally in nature, with few exceptions. They can turn around and form alpha helices or beta pleated, and all this is based on their hydrogen bonds. So you have then you have the tertiary structure. These alpha helices and tertiary structures can bundle around, fold around, and form 3-dimensional structures, which is really one of the biggest puzzles today. We know primary structure, we can make the structure, we can synthesize this, we can also see the secondary structures happening with some little bit of more accuracy and prediction. But how these will ultimately fold to give you a 3-dimensional structure is still a big question. One of the problems for research. And quaternary structure, how these three-dimensional structures bundle together and form one unit of the enzyme. Typically, you will see when people discuss proteins, you can have these ribbons or these helices and flat structures which depict the secondary structures. So we are dealing with this at the molecular level, but every time we need not really worry about the purification and the structure. Although in our work, we have actually done biotransformations using whole cells, and then we go on to purify the enzymes, as I will tell you. So the title of my talk is From Whole Cells to Enzymes. What I mean is, we have taken the whole cells of a yeast, Candida parapsilosis, I'll tell you why, and we have used it to make many, many optically pure molecules. We have then gone on to purify the enzymes, get the crystal structure, and study the mechanism at the molecular level. Now, biocatalysis, of course, is not just that it's telling you how fantastic nature is in making and biosynthesizing molecules, it's also the most promising technologies for the sustainable synthesis of molecules of pharmaceutical, biotechnological, and industrial purposes. I just told you penicillin and steroids all bank on only a whole lot of fungus, which does the job. Most of your antibiotics are coming out of fungus, big, huge reactors where the fungus is used to make these molecules. So if these enzymes are so efficient, then is it not obvious that we should use them for organic synthesis? And since the 90s, there is a steady increase and a lot of emphasis on using these enzymes. And more recently, about 2 years ago, it was honored by a Nobel Prize to Arnold Francis in Caltech, who's done directed evolution of enzymes and reduced multi-step organic synthesis to just a one-step enzyme synthesis, which I will mention a little later. So nature is the best teacher. It is truly amazing, and we have been looking at biocatalytic reactions for the past 3 decades and more. We used lipases to start with and other just into 6 classes, and you have oxidoreductases, transferases, hydrolases, lyases, isomerases, ligases. And this is based on the reactions they do. So the name clearly tells you oxidoreductases will do oxidations and reductions, which is what I'm going to concentrate on. So the work started with, actually in industry when I was working, they needed this optically pure molecule, which is an intermediate in antihypertensive drugs known as the pill drugs. Now, they were not worried about using it optically pure then, but recently, or well, about 10 years, 15 years ago, there's more emphasis on using one or the other enantiomer. So this was the racemic one. You can see this carbon is racemic. And this was the molecule which we were interested in at that point. But then I realized that this can be either S or R. And we decided, since I was invited to head that lab, biocatalytic lab, bioorganic lab, they called it, we decided we would standardize a method to make these optically pure. And if this is the target, either the R or the S, you can get it if you asymmetrically reduce this prochiral ketone, alpha ketoester, or you resolve this by a conventional method. This is the retrosynthetic strategy. And what we did then was to use a lipase, which is a hydrolase. It's not an oxidoreductase. I'll come to oxidoreductase. You can use a lipase to resolve these molecules, and you can get optically pure in about greater than 99% EE, or here 90% EE, which is enantiomeric excess. And you can see that both the enantiomers are formed. Now, this we published, and it is very gratifying today that this is a textbook material. This is one of the great satisfactory things about research, when your material actually goes from research paper to a textbook. And most people use this method now, using lipases for resolution of secondary alcohols. We also tried to do the prochiral ketoester and used carrot cells, which were very readily available in another part of the same industry, the tissue culture. That gave us one R enantiomer. And if we use the candida, which we already were working on, had started working on, that gave the S. So this gave us a great handle to generate our own standards. So we had the R and we had the S. And you know, to determine R and S, it's fairly simple. If they are reported, you just do the optical rotation measurements and you know what you have. In addition, we also do the characterization using extensive spectroscopic methods. So this is what we did with lipases. In the case of this particular molecule, an inspiration from this earlier published paper of S12-pentane diol by the Japanese in 1990 showed us that these guys actually produced only one. They were not losing one enantiomer. They were getting only S enantiomer if they did what is called a deracemization reaction using a candida. This is this paper reported here. So we decided, let us see whether this molecule also can get deracemized. What would be the advantage? I would be using the racemic OH, which is not very difficult to prepare, and I would not lose any enantiomer. I would get only one enantiomer, hoping that it is the enantiomer that we want. So this what started our journey using Candida parapsilosis. It was bought from the American Type Collection, and it was wonderful because we realized that this Candida is so rich in oxidoreductases, and we used it to make many compounds. By asymmetric reduction, we have this molecule, the chlorohydroxy compound, which is an intermediate for another molecule, which is used to lower cholesterol. We had amines, we had diols. By resolution, we could have amino acids. Oxidation was done. Deracemization gave us a whole lot of other chiral synthons. And amides, amines, ketoesters, hydroxyesters, ketoacids, all kinds of molecules, aliphatics, aryl substituted, heterocycles, everything was carried out. And today we have more than 250 chiral synthons just based on wholesale Candida parapsilosis. This is what it looks like. It's a cute little, looks like beads. It's not pathogenic. and this one is the 40x under the microscope. So it's a yeast, and all you have to do, it's not even fermentation. You grow the cells, you keep them, you monitor the growth. Of course, initially you'll have to screen for which is the time point which gives the maximum conversion. After that, you grow the cell, just harvest it, centrifuge, harvest it, get it, resuspend it in a buffer and use it as a reagent. So it's not a continuous fermentation. It is what is called resting cell reaction. Very easy to do, except a lot of optimization and a little bit of patience. So this, of course, like I already told you, this was a very, very wise thing to do with Candida. Use it for asymmetric reduction and generate a whole lot of molecules. So deracemization works, resolution works, and so does asymmetric reduction. You have only in deracemization, you get quantitatively only one isomer. Going back. So this was very important, and this was also very exciting to us. But for the sake of the students, I want to tell you, just getting the product was not enough. So with the help of a lot of my students, we managed to actually elucidate the mechanism of this reaction. This is almost magical. You put R and S and give it to the Candida, it generates only S. So what was going on? How are we going to propose a mechanism? That was the question. And we decided we are going to say that since it uses a cofactor, it's an oxidoreductase, we will have a keto intermediate, which will then go to the hydroxy again, which will get reduced, and you will get the 50% which is not oxidized plus the one which gets oxidized, which is why you get only one enantiomer. So this was done with the help of deutero compound. We made the deutero compound, and we saw that in the whole reaction, we could get a product which had H, which meant that D was being lost somewhere in the mechanism, which is bound to happen if it goes to keto and gets reduced again. So you get the H. So this intermediate keto ester, which is involved in the reaction, was confirmed by NMR, and it can form only if there is enantioselective oxidation of the starting material. Another proof came from the fact that we generated this methyl derivative, and if there's no H here, there's no oxidation, and therefore you will not get the desired product. So we nailed the mechanism. It's like a big jigsaw puzzle. I want the students to think that all this is like a big jigsaw puzzle. You are only putting the pieces together. This, of course, is the ethyl 4-chloro-3-oxobutyrate. I brought this example to show you that this is another very striking and amazing and simple thing actually. If you grow the biocatalyst in glucose, it gives you one enantiomer. If you grow it in glycerol, it gives you the R enantiomer. This, I told you, is an intermediate for carnitine, which helps in lowering cholesterol. This paper was very well received, and what they decided to call it was medium engineering to control stereochemistry. So enzymes really do wonderful things using stereochemistry. Now, I already said that one step should be enantioselective oxidation. So we wanted, this is the one. Yes? Hello? Are you listening to me? Hello?
Yes, ma'am.
Yeah.
Yes, ma'am.
Yeah.
Yes, ma'am.
Oxidation was one step which goes to reduction. So we decided, okay, we've had lots of examples with deracemization, asymmetric reduction, and resolution. Let's look at oxidation. And of course, the student did wonderfully well because she actually got regio and enantioselective oxidation of diols, something which the industry wanted. So we had a lot of industry interest in this. And more importantly, you get an aldehyde and which doesn't go to acid. And that, of course, is very attractive to them. They wanted a system which will give them aldehydes so that there is controlled oxidation. A lot of aldehydes are useful in the fragrance industry, flavor industry. So these are just to show you that, lots of papers, lots of PhDs who did their work and enjoyed using biocatalysts. And we didn't let go of this Candida. Some students are still working in IIT Madras trying to finish their PhD. looking at how some of these enzymes are working, as I will show you. So all this happened using whole cells. That is the entire cells. I told you, you can grow them, harvest them at the proper time, then use them as a reagent. Just resuspend in a buffer and use them as a reagent. Then came the stage where we wanted to do more, and we went on to purify, clone, overexpress, purify, and do the characterization of some of these alcohol dehydrogenases from this candida. And we have first, as the first candidate, we got what we call CPCR. It is the R specific carbonyl reductase. And we saw that it likes aldehydes over alpha ketoesters, and then lastly, it prefers ketones. This is the gold standard. This is the gold standard in the lab to understand this reaction. And all these alcohol dehydrogenases require NADPH as the cofactor. And this is what was purified. This is a gel picture to show you how pure it is. This is the reference for the molecular weight. And if you ask the student, she will tell you how many times I made her do it so that I could see this overloaded only one band. It is pure. That shows it is pure. If the subunit is 40 kilodaltons, optimal pH 7.5, works at 30 degrees. It contains zinc and it is dimeric. So this is what was the first enzyme. Then the same enzyme, we got crystal structures, and we actually did the crystal structure determination in collaboration with a friend, Professor Gautam, from the biophysics department in Madras University. Nidhi is the student who did this. She's working in an industry in Mumbai doing biocatalysis, and after her postdoc in Israel, she quite enjoys it. So this is what this enzyme actually looked like. Lots of alpha helices, the Rossmann fold and stuff like that, which I will not get into. What was our idea? We wanted to see how the R and the S enzymes will differ in their structure, because of which we get an R or an S specific molecule. But that is still not quite answered, because, structurally to study these things is completely non-trivial. Another student wanted to really figure out what was zinc doing in this enzyme. And it's not one zinc. One zinc we can understand in the catalytic site, because metalloenzymes will then help, the zinc will help catalysis by its electropositive. It will coordinate with O and make the C double bond O more amenable to attack by the hydride. That we can understand. But what was the other zinc doing? So we have two zincs. One is catalytic and one we found is structural. What is the structural zinc doing? I told you this has two units. It's dimeric. This looks like the structural zinc is holding those two together. But how do we prove that? That is what the question was. But before that, we also had to understand what is the stoichiometry of zinc per subunit, because in the crystal structure, sometimes the metal doesn't appear. This is the holoenzyme, this is the apoenzyme, and you can see that we really don't see the same thing in both pictures. So we struggled, and we did some little bit of side-directed mutagenesis and found that we are really looking at zinc, which is tethered to 4 cysteines here, and over here, this is not as, the catalytic zinc is not as conserved, because the enzyme wants to do its catalysis. Zinc could be anywhere with histidine, with cysteine, glutamine, or cysteine, aspartate, and 1,2-water, as it also happens in carbonic anhydrase. But in this case, the structural zinc must have the 4 cysteines. So this work led us to a lot of interesting things, including side-directed mutagenesis. Some of the questions are still unanswered. We're still working on it. And Vinay is the student who's presently working in Biocon. He's finished his PhD, but he's promised that he is going to write up the paper, results of which we have. Suffice to say that we might have some answer on what the structural zinc is doing. Our initial hunch that it was combining the two subunits may be quite right, but that it is so critical for catalytic activity is coming to the fore now after doing the side-directed mutagenesis. So this was the work on CPCR. And this is the same thing. Why does structural zinc have to bind to cysteine is another related question. Why does nature want cysteine there? It has sulfur. Zinc sulfur bonds is what it's aiming at. We still want to understand completely the role of zinc and where it binds. Also, another question I might tell the students over here, I have been wondering, when proteins get synthesized, when does the metal get incorporated in the protein, in the enzymes? A lot of enzymes use proteins. We know iron is there, magnesium is there in plants, iron is there in blood. And not just that, there are many metals which are there in the body. So at what point does metal get incorporated? I really don't have an answer. I would like to get an answer to that question too. After protein synthesis in the cell, there has to be some step which puts the metal where it's supposed to be. So that is a question. Then we come to the recombinant S-specific carbonyl reductase. We did the same kind of strategy. Both these are recombinant enzymes because my student Nidhi and then Sneha decided that, ma'am, this is from the wild type, it's too tough, we'll just do recombinant. So I said, go ahead. And we used the template and we got the S-red, again, very pure enzyme, you can see. And it, unlike the previous one, which likes aldehydes, this prefers alpha ketoesters, ketones, and then aldehydes. So the substrate preference is reversed. And it is a 30 kDa protein, pH 5 and 25 degrees. It is metal independent. Question was, is it a dimer or a tetramer? So this doesn't like metal, it doesn't have zinc. And what is the difference between the substrate binding for alpha keto esters and ketones? So what Sneha did was, she found that for these ketones, the Michaelis-Menten kinetics looks very much like Michaelis-Menten, but this tells us that there could be cooperative binding. Now, this was a little strange, even though the journal loved what we were trying to say, that two different substrates, same enzyme, two different kinetic models. So the enzyme also knows that these probably substrates are not native, not what it's designed for. This is probably a slightly promiscuous activity for this enzyme. And having said that, therefore, these kinetic models are also different and can be explored further. But we stopped at this point, tried to see whether we could get crystal structure. That didn't work, but we did our work with quantum mechanics studies and a lot of calculations with the help of Professor Michael Gromia. And we found that sometimes it's important, when you don't get the crystal structure, you can conclude something of the active site from the QMMN studies, molecular mechanics, quantum mechanical studies. So that put an end to that, and Sneha is working in Bangalore. She's doing exceedingly well, has a family and is well settled. STS page is now showing you that we actually managed to get a wild type also. This was the work of Jerina, who's writing her thesis now. I didn't want to let go of this initial bug which had already bitten me, that we have to have the wild type S, because whole cell has a lot of S product. So there has to be an SADH which we need from the wild type. And sure enough, she did a wonderful job of purifying it. You can see this is the contrast of the S-red and the CPCR, which we already talked about. The wild type is also 40 kDa. Look at this is 30 kDa. So we're looking at different kinds of different enzymes in this family. And this is tetrameric. This is also tetrameric, but this one is dimeric. This could be a cellular metabolism enzyme, or it could have mitochondrial functions too, as also these two, along with their biotransformations which we are seeing. So this is what we did with the wild type. And further on, we compared the three which we have. Do we have a crystal structure of the wild type? Not yet. I don't know if Jerina will do it. This COVID has set us back with quite a bit. I think she's winding up. She has enough data to write the thesis. So we have, I told you, this is zinc dependent. This is no metal. This is zinc dependent. So both these are zinc dependent. Interestingly, the recombinant S is not zinc dependent. Reduction pH is 6, here it's 5, here it's 7.5. And this also does oxidation. In fact, this wild type has shown wonderful results with oxidation also. So look at the cofactor specificity. This likes NADH, both these like NADPH. That's expensive. NADH is relatively inexpensive. So if you have to scale up these reactions using the pure enzymes, you want to use NADH, not NADPH, or you use a regenerating system, which is what is also demonstrated by her work. So we have now in our kitty three important pure enzymes from Candida. So one prefers ketone to beta ketone to aldehydes. That is the S-specific ADH. Then you have the recombinant S-red, which likes alpha ketoesters, ketones, aldehydes. Kind of similar. But the R likes aldehyde. So it may be an aldoketo reductase over ketoesters and ketones. And all these give you optically active alcohols. So this is wonderfully magical that we could do so much with these, with just one Candida. And many people asked me during my tenure in IIT Madras, so many years, so many people, so many meetings, why don't we switch to another organism? Well, there are two ways to look at it. You could also look at more organisms, and you could look at one enzyme and one organism and go deeper. And I think we stuck to this because the more we tried to understand it, the more it gave us and the more puzzles it gave us. So we were still working on it. And more recently, another student, Uma Mahesh, has purified an amine reductase from this. We had shown with whole cells that you can get optically pure amines. This is a very well cited paper of ours, surprisingly. And sometimes I want to also admit here that under pressure from students who want to leave early, you don't choose a proper journal. This could have been a really high impact paper, but I'm happy that it's cited so well. We published in a hurry because of the student saying that she has to leave. So anyway, that's the game of research. So you have this amine reductase from Candida. That was the clue. Whole cells give it, so there must be an enzyme which does it. And you can see that all these reactions have been standardized by this purified amine, and you can get a whole lot of amines, including proline, which gets reduced to the pyrrolidine. The kinetics were worked out. Here is the proof of purity from this enzyme. Work well done with Uma Mahesh, doing most of the work. He also showed that this amine reductase does alkyl amination, and the pHs for amine reduction and alkyl amination are different. So this is again very interesting because it could be considered as a promiscuous activity. And why am I harboring on this promiscuous activity? I'll tell you. So this is the keto acid or ester. This is the amine and this is the product. You can see it's become an amine and there's an alkyl over here. This keto has become an amine. Keto ester again, and you have the amines, you get the alkyl amine. This is what we mean by alkyl amination. Very important reaction. Reductive amination also can be done by this enzyme. This is the product. It just simply reduces, and you see that you can get very good specific activity with some products. Now, dehydrogenation, oxidation can also be done. The expected product is here. So there is lots which one can do with just tweaking the pH in one direction or the other. Most reactions will be reversible when done with enzymes. So you have to choose and optimize the pH at which you want. I showed you I can get oxidation and reduction with Candida pyroxalosis. Same here, I can get oxidation reduction using this amine reductase. So it's just a matter of doing it properly, doing it patiently, and understanding what it's all about. Now, up till now, this was our work, and we have done wonderfully well with this Candida pyroxalosis and all the purified enzymes. Amine reductase, we have the pure enzyme. We also have the crystal structure. I have not shown you anything here because Uma Mahesh is still working on it. He went to Indore. Here, I would also like to tell you that the country provides very good facilities. If you're interested in crystal structure, you can go to the center, the synchrotron in Indore, which is run by the Department of Atomic Energy. Just sign in there with your supervisor. They take care of all the expenses. You just have to travel there on your own and do your work and come back. So we're trying to solve the problem of the crystal structure of amine reductase. So we'll have 4 enzymes from Candida. Now, this is an important digression, although related to our work. I told you this was very nice when Frances Arnold got the Nobel Prize in Chemistry in 2018. What did she do? She did directed evolution of enzymes. What does that mean? Everybody here, I think, has heard the word evolution. So if life started with only one kind of cell, then to have such a complexity of diversity in life has to be accounted for. And that comes from the fact that enzymes or proteins over time evolved, but on a time scale of millions and billions of years. So you can actually imagine that all the amino acids in the primary sequence can be combined in various ways, and that takes time depending on the function, depending on the habitat, depending on so many questions and factors. So what they did was try to reduce the time of evolution. Can you evolve these enzymes, or can you do something to make the enzymes do the reactions you want to do, instead of waiting for millions of years to say have enzymes which will chew plastic and rid us of this plastic pollution? Will there be enzymes which will fix carbon dioxide, which is excessively there, harmfully there for us in the environment today? So they reduce the time by using directed evolution techniques, largely robotic, lot of automation, and lots of infrastructure and other techniques developed to do this. By and large, what you need to do is to notice and screen for promiscuous activity, as in go away from the normal activity of the enzymes, and even if has a slight bit of the other activity with the other substrate, try and amplify that. There are techniques to do that. When you do that, then you can get an enzyme which will do the activity which was less to start with, but you have managed to amplify it. Go to different habitats and isolate microbes and life systems from there, from where you can isolate enzymes to get wonderfully thermostable enzymes. You know, this is no longer true that enzymes work only at 35 degrees. You can have enzymes working at 100 degrees. You can have enzymes working at sub-zero, minus 40 degrees, depending on where you've got the bug, because you have life systems surviving in all these habitats. So it's a world out there waiting to be explored. And she's even sent people all the way to Yellow Springs, to the Arctic and Antarctic and whatnot, and isolated enzymes. But the notable example, which is really wonderful to see, is that you have this transaminase which is giving sitagliptin, which is an anti-diabetic drug. Normally you need a lot of process and you need a lot of rhodium catalyst to make this chemically. So chemocatalytic versus biocatalytic, and really transaminase the enzyme 1. This is a directed evolution enzyme from Frances Arnold's lab. Now look at this. So this transaminase was developed by Merck and Codexis for the manufacture of sitagliptin. Rhodium-based asymmetric hydrogenation of the enamine was replaced by this enzyme. And it was wonderful because you can see this is just giving a stereochemically important isomer. So you don't need to do anything, one step. And concerns over the fluctuating cost of rhodium and the compelling atom efficiency of the enzyme process meant the enzyme process has ultimately won. Now this lady in Caltech has something like 66 patents and industries which have taken technology from her lab. So it's little surprised that when they recognized application-oriented work, they honored her with the Nobel Prize. This is really worth reading what all she's been doing. I encourage students to go and read that. Another important example coming from this activity of directed evolution by her and other groups is looking at cytochrome P450 enzymes. These are a whole lot of enzymes which take care of all the xenobiotic metabolism in the body. What does that mean? Any compound, drug included, which gets into the system needs to be metabolized. So nature actually wants to make it more polar and throw it away, but can also oxidize, detoxify, and do so many other things. So this, by nature, these enzymes have lots and lots of functions. And they have engineered these to enable synthetically useful transformations, especially non-hydroxylation reactions, with improved enantio and regio selectivity. So you see, if you have a aryl hydrocarbon as a constituent of smoke, cytochrome P450 will go and put O there, OH there, so that it can get conjugated and can get thrown out of the body through urine. But these people have gone beyond just hydroxylation, and they have done reactions to transfer a carbene intermediate to an alkene to form a cyclopropane. Range of carbene nitrene transfer reactions, CH insertion of sulfonyl nitrines to form CN bonds. She has even got carbene insertion into a CSI bond. Now, CSI bond is a non-trivial thing. You can't form a silicon bond with carbon so readily. But an enzyme has been found which does that, and industry is really taking it up in a big way. As it shows you, all these are natural reactions, and all these today are non-natural reactions by cytochrome P450. It is so wonderful to see. And if you have a native enzyme which is doing this, here you have a little bit of an activity which I told you is considered promiscuous. You can really ramp it up and amplify it to get an evolved enzyme to do the new job. This is called directed evolution. Requires a different kind of a lab setup, but it's perfectly possible to do. I'm also proud to say that one of my students who finished PhD with me, Santosh Padhi, is working as an assistant professor in Central University, Hyderabad, and doing directed evolution and protein engineering in a big way in Hyderabad University. He has a few students also. The other person there is another student of mine in the chemistry department who's also doing a lot of work by enzymes, T. Sarvanan. So both these guys are in Central University. And of course, that brings me to the end of my talk on what we do with biocatalysis. We do other things like biosensors, biodiesel, and chirotechnology, which I've not talked about over here. But I have a lot of people to thank, both IIT Madras and IIT Jammu, all the funding agencies, the government, the industries who have over time being very grateful. We are very grateful. They've been very generous with us. All my students, past and present, who I absolutely hold in high esteem and respect. We have Department of Biotechnology, the Ministry of Telecom for biosensors, Tata Chemicals, Matrix, Ministry of Renewable Energy, DBT, CSIR, all these people who have funded us. These are some batch of students I recognize, and I'm in touch with most of them. They are the ones who make this whole exercise so very meaningful. Ever grateful. Thank you very much, but I have something else. I'm not leaving you as yet because I have to tell the students that we have a new opportunity in Jammu. We are starting an MSc program starting August 2022. If hopefully we don't have any more of this pandemic problem, this is where we are at. We are starting MSc and MS by research. This is 2 years, this is 3 years. The same lot of 20 students, 5 of them can opt for research and get a degree, another degree after another year. And the faculty has a whole lot of interesting areas and people, young faculty, Dr. Pal, Dr. Ramani, asymmetric synthesis, solid state, everything is there. We have Dr. Jairam for materials, Pankaj for asymmetric synthesis, organic synthesis, Shivnath, theoretical, computational, and Subhash, also an inorganic organometallic man. This is Dr. Vidya from industry, has huge experience with medicinal chemistry. And of course, this is me. We will be offering this. We have Dr. Piyush in the lab and Bhupinder Singh, who has also helped me make this part of the presentation. I'm thankful to him. And we have PhD program in chemical sciences, synthetic, organic, inorganic, computational, catalyst discovery and materials. Lots and lots of nice courses. I want to highlight that we also want to start this with the food chemistry, which I think is completely lacking in this country. Huge country, huge foodies. Every state has, every 20 kilometers has different food, but we know very little about food chemistry. Actually, my students don't even know what's the difference between a rasgulla and a gulab jamun. What's the raw material? I hope you guys know. If you don't know, I told them you don't have any business eating it. So we're going to start food chemistry, and we have bioorganic, bioinorganic, and the works. Who will get admission and how? You will get admission with your BSc. We are fine. You will have to come through IIT JAM, which is the joint admission test for masters, and you will have to go through the JAM the site and figure out how to apply. You can look at this, more than 55,000 candidates aim for admission to IITs, NITs, ICERs for the top MSc degrees. So those are the kind of institutes that you can get admission in. IIT Jammu is now included. Get the application form for admission. It is available in the website of JAM. You will have a test paper, and based on your minimum educational qualifications and eligibility requirements of admitting institutes, admission is possible. So we'll have 20 seats starting August 2022. We see you at IIT Jammu for MSc and MS Research. So thank you very much for your kind attention, and I'll take questions from anybody regarding our work. Thank you very much.
Thank you very much, ma'am, for this beautiful lecture. Any questions from the participants?
Hello, ma'am.
Hello.
Yes.
Yes.
A very nice talk, ma'am. Ma'am, actually, I want to know, have you recycled these enzymes?
Reuse them, yes.
Reused.
Yes.
What you do to recycle them, reuse them?
You just filter them out. Actually, one of the better ways to do it is to alginate them, encapsulate them, then it becomes easier. That we have done. So you alginate them, and then you can filter them very easily, and then resuspend and use them. Up to 10 cycles, they don't lose any activity. Then because of the alginate, it's a kind of a soft gel, it starts leaching out. So the activity goes down a little bit.
Okay, thank you, ma'am.
Sure.
Any other question from the participant?
Students must ask without worrying about what the question is. Every question is important.
Yes, students, you can ask any question from the ma'am. You cannot, don't think like that she's speaking too high on technical scale and you are not able to understand. You will ask you very simple questions related to your classes or anything related to enzymes, whether it belongs to high secondary classes or the college classes. So please don't hesitate and ask the questions.
Anything. You can even tell me that it was not understandable, and I will see what I can do about that.
Ma'am, the only thing that I wasn't able to understand was the mechanism of that ethyl 3-deutero 3-hydroxy 3-phenyl propanone.
Oh, I'm glad you asked that question. Can I spend a few minutes with this? Okay.
Yes,
Can you see this slide now? Yes?
Yes, ma'am, I can.
Okay. So this is an ester, and this is the beta hydroxy compound, right? We are interested in knowing how this deracemizes. How does the RS become 1 enantiomer? That was our initial goal. And our hypothesis is that it will get oxidized, become a keto compound, and then get reduced again. I don't have that slide over here, but I should have brought it. I'm sorry. But what you can imagine, this gets oxidized. How does it get oxidized? Imagine the NADPH nearby. What is NADPH? It is the cofactor sticking to the enzyme. That is important in all oxidation reactions, right? Oxidation and reduction reactions. So it can pick up this, itself get reduced. Okay?
Ma'am, actually, I didn't understand that. You said that when it is like the configuration will get S only. Yes, ma'am, that part wasn't able to understand that if the configuration is R and S, but in both the cases you said that we will get S only.
Yeah, so okay, so you start with R and S, and what our first point is that only R is getting oxidized. Okay, so this is R. Now, if R is getting oxidized, it will become keto. All right. And then there is another, the same enzyme, the S specific enzyme will reduce this keto and bring it to S. because the hypothesis is that the oxidation is for R and the reduction is for S. How did we conclude that? Because whenever we gave the keto, it always produces only S. When we gave R and S together, it still produces S.
Yes, ma'am.
So there is a preponderance or a dominant S reductase there. The oxidation is happening by another enzyme which is picking up only R.
Okay.
Right? And that is actually proved because of this oxidation. So once this becomes a keto, again you get hydroxy and the H after reduction. And this H can come only if the D is lost first, right? Then the H can come from the medium. And this we detect by NMR. So it proves that the keto has to be formed. And therefore, if the keto has to be formed, there has to be oxidation. If there has to be oxidation, there has to be R-specific oxidation. And because we are getting S, then we have to conclude there is an S-specific reduction or a reductase which is doing that. Got it?
Yes, ma'am. Thank you.
Sure.
Any other participant?
See, once this pandemic relaxes its rules and you can also visit the department sometime. Good, Pri?
Yes,
You're
ma'am.
more than welcome with your students to come and see, especially the Flora
Hello, I have
campus.
one question.
Yes.
Is there any scope of enzymatic reactions in total synthesis or multi-step reactions?
Oh, yes, absolutely. Absolutely. I showed you the first example where we did this prill drug intermediate. No? So if you get this one, you can use one of these to make the prill, lisinopril and others, right? This is the one I'm talking about, right? This part. So it's certainly one enzyme, and then you can have a chemoenzymatic way. It's important to start integrating some of these enzymatic steps within the synthesis. This is what Francis Arnold is doing, right? This is also the same thing. They bring it till here and then they do just one step to get sitagliptin. In one shot, it converts the keto to the amine in the right optical stereochemical arrangement.
Okay, ma'am. Thank you.
Excuse me, ma'am. Well, why
Yes.
did you use this Candida parasilosis? You had a special attachment with this fungus or like something like that?
No, I hope nobody is attached to any fungus. But I told you the inspiration was this paper. I was fascinated by this reaction that you have a racemic and it's giving you only one. Normally doesn't happen so easily, right?
Okay, ma'am.
So this actually, way back in 90 when we saw it, we thought we'd use that. And we used it we went really beyond this. I mean, we sort of left this behind and saw so many wonderful things, including amine reductases and all kinds of things there. Yeah.
Okay, ma'am.
Any other question, participants?
See, this Candida is a yeast, okay? And it's fairly robust and easy to handle. Sometimes these organisms and enzymes can be very temperamental. You lose activity very easily. You have to work a lot to just keep them alive. This is fairly okay.
I like your personality. I literally want to meet you someday.
Sure, please come. What's your name?
Ma'am, I'm Shweta Rajput.
Come. Whenever this clears up, yeah? I was also saying that I would like your students to visit the Flora campus of IIT Madras. We're still holding on to that. All the lovely instruments are there. Looking at that, I thought I must be 10 years or 15 years younger. I would love to start doing all that again, playing around with those instruments. Beautiful microscopes, SEM, TEM, NMR, HRMS, everything is there. Yeah.
Is that okay from all the participants? Do we have some more questions? I think, ma'am, it's okay from the participants' side. Thank you very much, ma'am, for sharing this wonderful piece of presentation with the students. And students must be encouraged, especially we are at different college, and they must have got inspiration from you and your age. That at this age you are so active at your research, and the way you interacted with the students might have encouraged them.
Oh, you know, it's an absolute plus. I believe that for any teacher, anybody in this line, it is the energy from both sides which actually is important. And I love to see students who join me at time zero to find by the time they finish their PhD at 4 or 5 years, completely different, wanting to do things, confident, you know, getting jobs. We will do this. That's what we want. Instill in them tremendous amount of confidence. Yeah.
We had planned this conference in the way that we wanted you to interact with our students. And
we'll come. We'll do that. We'll do that, Gurpreet, when this clears up.
Yeah, just because of this upsurge, that very sudden upsurge of the cases, we could not hold that, but possibly, definitely in future, we would like you to visit the campus and interact with our students and motivate them.
Sure, would love that. And I would like to see some of the students come for MSc. Yeah.
Yes, ma'am, yes. Ma'am, here is a request from my side.
I can't hear. I lost you, Gurpreet. Hello?
Ma'am, I think has been offline.
Oh, I didn't hear the last part of what she was saying. Yes, I can hear you.
Okay, maybe network issue at my end. Ma'am, there is a request from my side that the students in our college, they are not much accustomed to the exams that need to qualify for getting admission in this IITs. I request you, please guide our students after the session. Maybe someday else we can have a special meeting for how to crack this jam for MSc.
Yeah, before that, what we can do is look at some sample papers from JAM. Just look at the chemistry papers from JAM and see, make an assessment, and certainly faculty over here also would be happy to interact with you guys, everybody in the chemistry department. We'll take that up.
Thank you.
Sure.
Thank you very much. Thank you very much, ma'am, for sparing your valuable time and
pleasure.
Sharing your